Last episode, gradient descent gave us the recipe. To learn, take a step against the gradient. But we waved our hands at the hardest part. To take that step, you need the gradient, the slope of the loss with respect to every single weight, and a real network has millions of them. Today we answer how you compute all of those slopes efficiently. This is backpropagation, the most elegant idea in the whole field. Here's the problem in numbers. Suppose you have a million weights. The obvious approach, nudge one weight, run the whole network, see how the loss changes and repeat. Once for every weight. That's a million full passes through the network just to take one step. With billions of weights, it's hopeless. We need a way to get all the gradients in essentially a single pass. The whole trick rests on one rule from calculus, the chain rule. It says if you chain functions together, the slope of the whole chain is just the product of the little local slopes along the way. How sensitive is the output to the input? Multiply how each step affects the next. That's it. Backprop is the chain rule applied carefully to an entire network, because that's exactly what a network is. A chain of functions. The input flows into the first layer, whose output flows into the second, into the third, and finally into the loss at the very end. Each layer is one link. To train, we need to know how the loss at the end depends on the weights way back at the beginning. The chain rule is built for precisely this. It happens in two sweeps. First, the forward pass. The input flows through the network layer by layer, each one computing its output and, crucially, remembering it. By the time we reach the end, we have a prediction and we have every intermediate value stored along the way. We'll need those in a moment. At the end of the forward pass, we compare the prediction to the truth and compute the loss, that single number for how wrong we are. This is the starting point for everything that comes next. Learning doesn't begin at the input. It begins here, at the loss, and works its way backward. This is the backward pass and the name backpropagation. We take the error at the loss and push it backward through the network, link by link, right to left. At each layer, we ask the same question: how much did you contribute to this error? The answer flows backward, getting handed from each layer to the one before it. The reason this works is that every node knows one simple local thing: how its own output changes when its input changes, just its own little slope. A neuron doesn't need to understand the whole network. It only needs its local gradient, the derivative of its own operation. Each node minds its own business. And here's where the chain rule pays off. To find how the final loss depends on an early weight, you multiply the local slopes all the way back from the loss to that weight. The error signal arriving from the right times the node's own local gradient gives the gradient for that node and what to pass further back. One multiplication per link. There's a name for the quantity flowing backward, the error signal, often written as delta. For each neuron, delta says how much that neuron is responsible for the final error. High delta, big share of the blame, adjust it a lot. Near zero, it was basically fine, leave it alone. Backprop is, quite literally, an algorithm for assigning blame. And now the punchline, why this is fast. When backprop computes the error for one layer, the layer before it reuses that result. Instead of starting from scratch, the work flows backward and is shared at every step. So instead of a million separate passes, we get every gradient in just one forward pass and one backward pass, from hopeless to almost free. Make it concrete with three nodes. Forward, A feeds B, B feeds C, C gives the loss, numbers flow left to right. Backward, start with the slope at C, multiply by B's local slope to get the gradient at B, multiply again by I's local slope to get the gradient at A. Each gradient is just the one after it, times one local derivative, right to left, multiply as you go. So here's how the pieces fit. Backpropagation's only job is to compute the gradient, the slope for every weight. Then gradient descent takes that gradient and does what we saw last time. Step against it, scaled by the learning rate. Backprop finds the direction, gradient descent takes the step. Together run millions of times. That is how a neural network learns. That's backpropagation. One forward pass to make a prediction, one backward pass to assign blame, using the chain rule to share the work. It's the algorithm that made deep learning possible, and it's running right now inside every model being trained on Earth. But that plain step against the gradient can be made much smarter. Next time, optimizers from basic descent to Adam. See you there.